My name is Peter, and I'm here with Gauji today. And today we want to talk to you about how we scaled PYMK, one of our key recommendation services. So what is PYMK? PYMK is our People You May Know service, and we'll start off with an overview of what PYMK is and what it means to LinkedIn. And then we'll talk about Venice, which is one of our key data infrastructure components of PYMK. And we'll move back and talk about the evolution of PYMK, from its historical form to its current form, and how we scaled it for the future. And we'll end with some of our results and key learnings that we took away from this journey. Before I get into too many technical details, I want to step back and tell you about LinkedIn's vision. So really, here at LinkedIn, our vision, our mission statement, is really to create economic opportunity for every member of the global workforce. So I'm sure that some of you out there have found jobs, have found opportunities through LinkedIn. I know personally myself, I found my job at LinkedIn through LinkedIn. So it's kind of meta, but I think it's a pretty good example of what we're talking about. And really, so a key part of enabling that is helping members to grow their professional network, which helps them to connect and stay in touch with others in a professional context. And PYMK helps members grow their professional networks by recommending other members to connect to. So really, by helping members grow their network, we can also help to improve their experience on the site. So for example, when you go to apply to a job on LinkedIn, we can reference connections that work at that target company. So having a strong professional network is really key to helping members realize their full economic opportunity, and PYMK is the foundational product that helps members achieve that goal. So in order to understand how PYMK works, it's going to be necessary to understand how Venice, one of the key components of our systems, works. So for that, I will turn over to Gauji, our resident Venice expert.
Thank you, Peter. So our Venice had been developed inside LinkedIn for more than 3 years, and we deployed .NET cluster in production, and Venice is performing 10 of million lookup every second. So this is our vision of Venice. It is a key value store with a scaling capability. So before diving into detail about Venice, I want to share some short story about Venice. The project name actually named after the Venice city, so which has a lot of stream inside, and it is aligned with the motivation of Venice to have the proper streaming processing support. And the logo is actually wind line. It's similar to the Venice city logo flag. So as a key value store, so Venice has some major difference from the one in the market. Venice was designed as a derived data platform in the beginning. So as a derived data platform, Venice does not support the direct update, but most users use to store the derived data, which are computed either offline or in real time. So machine learning job is a perfect use case for Venice because all the data processing is asynchronous. But the challenging part is data volume is really huge. So we have tuned Venice excessively to support the highly throughput ingestion. And after the data was processed in Venice, the Venice customer could use the Venice client to perform the single get and batch get API, retrieve the data back. So Venice guaranteed fast data lookup. For the single get, Venice guarantees single-digit millisecond lookup at P99. And for some special large batch get, we have tuned to offer less than 50 milliseconds at P99. And inside LinkedIn, we also make the self-onboarding very simple. So the customer could use the self-onboarding tool, easily define the Venice table, define schema, evolve schema very easily. So I want to use this table to describe the capability of Venice about ingestion. So the left header of this table is used to describe the data processing component we are using. And the top header, it is the ingestion mode. At the very beginning, Venice only supports the batch ingestion through Hadoop, which is very similar as the one we have in the past, the original system called Watermont, but LinkedIn opened source many years ago. So with the batch push, the Venice customer could bulk load a whole data set into Venice very quickly. So later, we introduced this streaming processing. As I mentioned earlier, one important motivation of Venice is to have the proper streaming support. So inside LinkedIn, we are using Samza as the real-time processing framework to support the streaming job. With streaming job, you can continuously update the existing database. So we are keep filling the table. As you can see, we are, as the new requirement come, so we introduce the Hadoop incremental push job on top of the Hadoop batch push job. With the incremental push job, the customer will be able to update data much faster. And we also introduce the Samza reprocessing job, because inside linking, some customers only use Samza to do the data event processing, not Hadoop at all. So when their processing logic change, they have to reprocess all the event in the past. So one is introduce the reprocessing job to support that requirement. Semantic-wise, it's similar as the Hadoop batch push job. In the end, we introduce a new data model we call the hybrid. So essentially, hybrid is the combination of batch push plus streaming processing. So this batch push could either triggered by the Hadoop batch push job or the Samza reprocessing job. So as you can see, this is architecture very similar as the traditional Lambda architecture, which consists of a batch layer or speed layer. But the key difference from that one is that the data merge. So Venice is doing the data merge during the ingestion time, and Lambda normally do the data merge in the read path. So with this way, we think the resilience is better, because every lookup you don't have to only rely on one database instead of two. And the performance is also better, because every query only involves one lookup instead of two. PYMK have been a major customer from the beginning, and we want to share the several use cases in the PYMK application.
So now that you all know about Venice and how we're using it, I wanted to talk a bit about how PYMK has used Venice throughout its evolution to its current form. So first, in its original form, so really the PYMK, the problem is how to get the PYMK recommendations for each member. So we can sort of break this down into several phases: candidate generation, feature generation, and then scoring. So in the early days, all of this was done offline, or as some of you may know, offline inference. So the candidate generation phase is essentially, we need a way to produce a viable subset, since we cannot possibly rank or score every other member for every other member. That's sort of like an n squared problem. It just doesn't scale. So once we've done candidate generation, we can now retrieve the features or the attributes for each candidate that will then be used to feed into our model, which will do the actual scoring and ranking. So as I mentioned in the beginning, all parts of the system were done offline in our Hadoop cluster, and all the results were pre-computed. So this would essentially be computing the top K recommendations for each member. So sort of the flow looked like this. Once we have the results from our offline job run in our Hadoop cluster, we're going to push the results to a Venice store. And these results will be keyed by member ID. So essentially, you could think of the key as the member ID. The value would be the top K recommendations for that member. Thus, when looking up a member's PYMK recommendations when they come to the site, is just a simple key value lookup. And I'm using air quotes for simple, because those of you who've worked with scaling key values stores will know it's anything but simple. But from the PYMK point of view, it was simple. So our online service here was very straightforward. As you can see, at request time, it's a straightforward operation. But it does have several drawbacks. Number one is staleness. This monolithic offline flow that I described could take several days to run. So we cannot incorporate changing features that well. Also, you can also see that this would waste computation potentially, because we are pre-computing the recommendations for every single member. We may be computing those recommendations for members who don't visit the site. So as we started to look out to see how we could break up this offline monolith and start to move things online, we started to look at each phase. So number one, for candidate generation, we continued to use the existing offline flow and treated that existing Venice store as one source of candidates. We then augmented it with other online candidate generation sources. We have an online graph database called Gaia, which is able to do something called real-time triangle closing. And we can use this as another source of candidates. Similarly, for feature generation, we created a new offline flow to generate the features which we wanted to use online. Those features were then pushed to a new Venice store. We also augmented this with Pinot, which we use for real-time aggregation-based features. and we keep that up to date via Kafka. So all of this really helps reduce staleness. And so tying everything together, you can see this is sort of what our architecture would be online right now. So as a request comes in, the first thing we're going to do is generate those candidates, both by retrieving from the existing Venice candidate store and also by generating some candidates from Gaia. Now, at this point, we're actually generating thousands of candidates. So during the feature generation phase, we need to pull back the features for all those thousands of candidates. Only at that point can we then score and rank and return that response as your PYMK recommendations. So this online service was great in that it tackled those two problems I mentioned, staleness and potentially wasted computation, but it did introduce new challenges. And the main challenges was retrieving that amount of data in terms of the features at request time. So you can see for a single request, because we're generating potentially thousands of candidates, we're needing to pull back a ton of feature data in order to score and rank those candidates. So you can see there's kind of along the read path, there's this huge read amplification. So next we want to talk about how we optimize this feature retrieval from Venice.
So inside Venice, we treat as this one as an online feature retrieval use case. It's kind of special because, as you can see, as Peter mentioned, that every request could contain about 1,000 keys, really large query. So, so we did an experiment at the very beginning. So the base latency about 4 seconds at the P99, which is completely unacceptable. So we did some tuning. For example, we switched from the original pure Java storage engine to the RockDB, which is offline off-heap storage engine. We were able to bring down the P99 latency to 60 milliseconds. And the reason we think with this off-heap storage engine, RockDB, it's because it's minimal GC overhead. And with RockDB, we can adopt reverse, cache strategy. And what we did, we try to keep all the data in the memory so that we gain this so fast data lookup end to end. And since right now we have solved this case properly. And next, we want to present a new, a new challenging use case.
So as we look to improve the quality of your PYMK recommendations, we're always iterating and improving on our models. And this creates new challenges for data infrastructure. So some of our newest models, they further increase the demand for data at runtime, both as the number and size of those features have increased. So our latest models, they needed to incorporate something called embeddings as features, which are essentially dense vector representations of our members. And this presented another challenge in retrieving even more data at request time. So I wanted to give a brief overview of what embeddings are. So embeddings, they can have a slightly different meaning in different contexts, but generally in ML, they're going to refer to a dense vector of real numbers, which are associated with the entities that they represent. So as an example, for our entities, we're considering members in a connection graph. And for each member, we can learn a vector representation of those members. And this representation is learned such that if two members are close in that initial connection graph, those vectors would also be close in the resultant vector space. And that closeness, it might be measured using something like dot product or a cosine similarity measure. The point here is that this cosine similarity can now be used as another input feature. And this results in what we call a pairwise feature for the similarity between two members, a source and a destination. And this is really valuable to us because these embeddings, they're able to summarize a lot of information about the member, their place in the graph, and their attributes. So now that you're all experts on embeddings, I can talk a bit more about how we decided to use them. So we wanted to use this similarity between the viewer and the candidate as another feature for our next generation models. So it's very difficult to pre-compute this similarity measure because, again, it would be sort of like an n-squared problem. You would need to compute the similarity between all 630 million plus members. And we decided that was just not feasible to do offline pre-computation for that. So in the online world, again, we're typically evaluating thousands of candidates at request time to produce those recommendations that you see. Not all possible pairs, but thousands. So since these embedding vectors that we are generating are typically on the order of 10 to 100 dimensions, where each element is a float, and each one is associated with each member. So now for a single request to PYMK, we're having to pull back thousands of these vectors under our current batch get model, one for each candidate member and one for the viewer. And so you can kind of see if the QPS to PYMK is quite high, this is going to place even further demands on that data transfer between our Venice store and PYMK. And essentially, this was creating a bottleneck in terms of not only the network utilization, but also the deserialization overhead. And this was not really sustainable under our current architecture. So we started brainstorming with our data infrastructure partners, and one of the things that we thought of was, or one of the things that we sort of arrived on was that typically models are developed, like ML models are developed typically without consideration for the required network bandwidth and overhead to retrieve those features at scoring time. So we were thinking what if we could make this implicit assumption true. So instead of bringing that data to where the computation was being done, what if we could push down that compute to the data? And this would help us in this case because typically the result of that computation, i.e. a cosine similarity, is just a single scalar value, whereas the inputs are these huge, potentially 100-dimensional vectors. So if we can push down that compute to the data and just have to return that similarity score, we're reducing that overhead by a factor of 10 to 100 times. So we'll talk a bit more about how this was implemented on the Venice side.
Sure. So as you can see, this embedding use case is sharing the similar exercise pattern as the previous one, still large batch get, and at peak time is minimum lookup. The only major difference is the value size. It's 10 times bigger, as Peter mentioned, that because it contains multiple dense vectors. So without any change, the base latency is about 275 milliseconds at P99. And with the server-side computation we discussed, implement, we are able to achieve the 60 milliseconds at P99. So there are multiple reasons to get this huge improvement. The first one is much smaller response size, because after compute, the input is a dense vector, but the result is just a scalar, much smaller. And the second one is about the parallel computation inside Venice, because inside Venice, we can distribute the request to all the server nodes are hosting the same database to perform the parallel computation, which makes it even faster. So with the server-side computation, Venice only supports simple vector optimization constraint. So as Peter mentioned that so far we only support the dot product, constant similarity, but more operation coming. And right now, Venice does not support the arbitrary, or we don't allow arbitrary computation, because we think arbitrary computation is really hard to understand and not easy to tune. Well, actually, we did not stop there. We did more tuning in general. So Venice is heavily using Avro as an underlying protocol, and the regular Avro implementation is not performing well for the serialization, deserialization, since every time it has to look at the schema to decide the action for each field. Internally, it's more like a strainer machine style. We adopt this fast Avro library, open source by RTP House. Essentially, it's doing the real-time code generation to build a faster encoder, decoder implementation. On top of the original fast Avro library, we did several enhancements. So the first one, we introduced the legacy Avro version support, because inside LinkedIn, there's still many applications are still using the legacy Avro version, for example, Avro 1.4, for some historical reason. And we also introduced the object reuse for the deserialization, which is a standard feature in Avro. And we also did some special tuning, which proved very useful for vector operation. So with all those optimization, we changed our architecture in the following way. After we introduced the compute, this is the high-level architecture. Venice is employing the 3-layer architecture. The PYMK is using Venice client, talk to Venice router, kind of like a Venice gateway. And every computer request to Venice router will go through the scatter gather pattern. So Venice router will find out the request to all the server nodes, which are hosting the same database. So Venice server node will perform the data lookup locally and execute the required computation return the response back to the router. Router will consolidate the response to a full response and return back to the client. So all those tuning and all those improvements had made the online computation possible. And we also want to share the key learning we got along with the journey.
Right. So some key points to take away here that we discovered is moving the compute closer to the data was helpful for our PYMK use case with relatively large numbers of candidates to score. Relatively large number of candidates to score, in comparison to the cost of the computation on that data. So moving that compute closer to the data helps scale this real-time computation for our embedding similarity. In terms of doing things online versus offline, we wouldn't say one is better than the other. It really depends on the use case. I described a lot about what we moved online. In terms of doing things offline pre-computation is okay if your inputs are not changing frequently and the output space is relatively small. Online may be necessary if your output space is large, especially for those pairwise features that I was talking about, where you're having to compute some similarity measure between a source and a destination. It may not be possible to pre-compute all of that. It could be very expensive and time-consuming. Also, if you needed to incorporate some sort of context-specific information only available at request time, those are some reasons that you may want to consider doing things online. And lastly, but not leastly, I do believe that the close collaboration between our ML and data infrastructure teams helped us arrive at an efficient solution. And so leading into that, this is certainly a team effort. It wasn't just Gaoji and myself. These are just some of the folks that helped us build out this solution. Wasn't enough space on the slide to list everyone. And lastly but not leastly, the fast Avro implementation that Gaoji talked about, we have open sourced it. Please do try it out if you are using Avro. You may see some huge improvements like we did. So please check it out. Give us a star, open issues, open pull requests. We very much appreciate it. And thank you all for your time. And we'll take questions now.